All right, so are we actually recording that? There it goes. It is recording. I forgot to start the recording. I'm going to do a brief rundown of what we've been talking about. Today we're talking about Ptolemy, Copernicus, and Kepler. This is our discussion of Ptolemy. This is a picture of his view of the universe. What we have here is this black thing is a sphere of what's called fixed stars. At the center is the Earth. Ptolemy had something that's now known as the Geocentric Theory. He believed that the Earth was at the center. He wanted to describe the motions of all the stars and the planets, and he understood that the sphere of fixed stars rotated one time every day, and that the sun rotated with it to provide the daily motion of the sun over the Earth. And he also believed that the sun traveled on a path called the ecliptic. That's this orange line right here. And it basically went along the ecliptic one time every year. It goes around once. And that provides the observations. And now we're talking about planets, which is the harder part. He wanted to describe what a planet was, and planets basically wander. Over multiple nights, if you observe where Venus is, it may do something like this. Okay? Kind of like curlicues through the sky, and he wanted to understand what was doing that. So his theory of how that worked just like this. So he said that, imagine that we have the following system. So I take a circle, and I say, the Earth, let's put it at the center of the circle. Okay? And over here, we want to put Venus. Okay? But we need Venus to basically sometimes be moving to the right and sometimes be moving to the left, right? If it's going to curlicue through the sky like this. And so in order to do that, he used something oh, Ash, if you have a recording, if you want to send it to me, that'd be great, actually. Yep. So he said, how do I make it so that sometimes it moves to the right and sometimes it moves to the left? And he had the genius idea of doing this. He said, suppose that I take another circle and I say this circle, we're going to put it kind of right there. And we're going to say, suppose that this circle, and he had a name for this thing he called an epicycle. All right. And he said, let's put Venus on that epicycle. Okay, so here's Venus. And he said, Venus is going to move around in a circle like this. Oh, whoops. Venus is going to move along this circular path, like that. But the epicycle itself is also going to move. Right? So the epicycle moves around in a circle, and Venus moves around in a circle. And then all of this, is, of course, is attached to the sphere of fixed stars, so that you can do one rotation. All right? But we're not going to worry about that part. Everything is attached to the sphere of fixed stars in Ptolemy's system, so it's like everything rotates once per day, right? Why does everything rotate once per day, really, by the way? Now that we know what's really going on, whatever that means. Why did he need this? Why does he need everything to rotate around one time per day like this? The stars, the sun. Huh? What about the Earth? Yeah, so that's our modern understanding, right? Is you don't need all this other stuff. You just say, oh, the Earth actually rotates one time per day, right? But he didn't know that. The Earth's not moving at all. Does it move? Have you ever seen it move? Is the Earth? No, I'm serious. Like this is the way they thought about things, because this is our home, right? We're at the center of the universe, and this is it. This is all there is. It's us, a sphere of fixed stars, the sun. The Earth is not moving. Yeah, exactly. That's right. Maybe I should have made that more clear. It is moving on its axis. I'm not trying to tell you it's not, but this is what Ptolemy needed to do to produce a theory that worked, right? So the epicycle with Venus on it, okay, this V stands for Venus, and the Venus would move in a circle like this, but the epicycle itself would move as well. So let's take this piece and then copy it and then move it down here. So after a quarter cycle, for example, and just depending on the rotation rate you need, now, I gotta erase some lines here, but, now the epicycle itself is, the epicycle itself is still moving, right? So the epicycle is moving this way, and Venus may actually now be, Venus may now be somewhere like right here. I don't know, somewhere. And it's still going around in a circle like this, right? So Venus does its own rotation. The epicycle itself moves around in a circle. And then what you can do is say basically that by doing this, sometimes Venus is going to be moving this way, and sometimes Venus is going to be on the bottom side moving this way. And that'll allow you to get this type of motion. And that's it. That's how he worked it out. Does that make sense? You guys have any questions? So you have this thing called an epicycle, Yeah, that's his theory. Basically. I'm leaving out a lot of details, but that's basically it. Does it make sense? You guys have any questions? Can you see how that would actually produce the motion that Venus is undergoing there? Okay. Now, I'm leaving out a lot of details of this, which are that in Ptolemy's theory, he needed to make a lot of adjustments. Was this rotation of Venus for one day? So the epicycle itself, like how long Venus took to go around one time in the epicycle, I don't remember what the number of that is, but I can guess it has something to do with the period of Venus's orbit around the sun. Something to think about here, though, by the way, is like, you understand that physics was not a part of what he was doing. It was only astronomy. So he didn't need to have a cause for why something like this, I guess the rotation of Venus around Earth. It's the rotation of Venus around Earth. Yeah. So this, I think that it would be that the epicycle would go around one time per day. I think this is right. While Venus would take a longer time to go around in a circle like this. Yeah, okay. So I think that's right. It's been at least 20 years since I actually read Ptolemy, though. So there's a couple of details I want to throw out here, first of all. I lied to you when I told you that Earth was at the center of his system. That wasn't true. He actually had to have the Earth off center. Okay. Now, why did he do these things? Like, why did you notice? There's a lot of circles here, right? It's a lot of circles, right? Why didn't he use any other shapes? So the reason he didn't use any other shape was kind of like because Ptolemy had one unifying principle. And that principle was uniform. No, let's not use the word uniform because that would be a lie. It was circular motion. He thought that uniform circular motion, Jesus, yeah, exactly. I was going to say uniform, but the reality is that'd be a lie. Because he had to do things like, he had to move the Earth off-center in these circles to make everything work right. And that was kind of weird. And then he also had to introduce new points. So there was another circle here, and then there's these 3 points. So you have the center, and you had this other weird point. I remember this being really controversial when we discussed it at my school. It's called the equant. And this thing was basically the center. I'm not going to write it. It's not that important. But the center of the circle was here, the Earth was over here, and then the equant was over here. The equant represented the point around which... I'm trying not to use modern language. The point around which the epicycle moved with uniform circular motion. I don't know if that makes any sense. What that means is the thing, basically the epicycle itself, it actually had to go faster over here and slower over here to make it all work. Okay, so these are the details that are probably not that important or relevant to you guys, but I just want to tell you that even within his own unifying principle of circular motion, he had to basically break a lot of rules about what circular motion meant in order to make his theory work. And I mention this because this is kind of how science goes sometimes, is that you really, really want this perfect, beautiful mathematical theory, but then when you start to apply that theory to the universe is like, it's not that simple, dude. Like, it's a lot more complicated. And Ptolemy was basically able to unlock a lot of these secrets because he was willing to kind of bend his rules a little bit, you know what I mean? He was able to bend the rules that he created for himself, that Aristotle created for him, effectively, because Aristotle believed that, I mean, it's worthwhile to say right now, he believed that the universe was made of 5 things. There were earth, air, fire, water. You've heard of that before, right? And each of those objects had certain rules about how it behaved. Earth was something heavy, therefore it fell to the ground. But there was a 5th thing, I believe he called it quintessence, or is that the wrong, maybe I'm confusing it. Was it quintessence? I don't know. And that was the thing that the heavens were made out of. The things like the stars, the sun, the moon, were made of something different. And the rules for how that thing works are this. Because you look in the sky and everything seems to be moving in circles, so you say, wow, I guess circular motion is the rule for our universe about the way that these things in the sky behave, right? So that was coming from Aristotle, and it was kind of the prevailing wisdom of the time was that anything in space has to go in circles, right? But then Ptolemy starts to bend those rules a little bit, because he's like, well, yeah, they go in circles, sure, and I can make this epicycle, and I can make it all work, and I can produce this appearance of what Venus does, But quintessence. Yeah, there's an N in it, but yeah, that's the word. I think that's right. He's like, it's not really circular motion because the Earth's over here and the epicycle's moving like this, and then you have to have this other point around which you say there is uniform motion that's off center, and it's like, yeah, I mean, it's kind of a mess, so to speak. But that's what science is. Like, I wish we could do labs because like I want to do the friction lab with you guys and I want to do the acceleration lab with you guys because I want you to see how all these things that I'm teaching you are just a first approximation to the truth. You know what I mean? Like, science is so much more complicated than it is in a textbook, and you will all realize this when you get jobs and start working on things, that in any physical system, the things you learn in your physics class are not ever going to work. The things we learn in physics guide you to the truth, right? They help you to understand the bigger picture, but the reality is that even the laws we teach you are slightly altered as you go further in your career, right? And Ptolemy was just one of the first people willing to do it, to look at data. Did somebody call Nergal? What's Nergal? I don't know what that is. Okay. So that's Ptolemy's system. I think you guys can all agree that it's quite complicated. It's not very simple, and but it worked. It really did work. Like, it really worked to describe where things were. There's more to it than this. The outer planets are even more complicated. If you want to describe the motion of Jupiter, you need to do all kinds of crazy things. You need to introduce something to understand why this retrograde motion occurs. You need to have multiple epicycles, and just, it gets real complicated really quickly, trying to describe the way the universe looks from the Earth, but it works. Okay. So, that's the first part of our story is Ptolemy. And this theory was basically the theory in science for thousands, like 1,000 plus years at least, I think. I have to go look up. I think Ptolemy's like, I don't remember the numbers, but it wasn't until Copernicus, and Copernicus is probably, I think he's like 1600s maybe. Maybe someone can look up when Copernicus died. So Copernicus is a, I can't remember where he's from now. I should have done my normal, reading up on history. 1543. Okay, thanks. Is that his death? The death is actually the relevant date here because his theory wasn't properly published until he died. Yep. Okay. So, Copernicus, alright, so, I don't know what you guys know about Copernicus. He's commonly considered to be the kind of father of the heliocentric theory of the universe, which is to say the father of the idea that the sun is at the center of the universe. Or the center of our solar system, I should say. I don't know how true that is, really. I know it's what we tell you guys, it's what people tell you, but the reality is he was not the first person to come up with this idea. Not even close. The Greeks thought about this. Ptolemy himself. This is the thing where people call Ptolemy the geocentric person that just they don't really understand what it was that he did. Even Ptolemy looked at his system, right? Just look at his epicycle. Look at his silly epicycle thing that he had to create, right? And he asked questions like, well, what's actually here? What is at the center of this circular motion? Oh, that's awesome. What is this? That's really neat. Wow, that's really cool. Thank you, Danielle. Look at it. That's so cool. There's the epicycles, right? This is exactly what Ptolemy's system is like, right? All these little epicycles. This is the Earth at the center, right? Yep. Where's Venus? Here's Venus. Look at that. That's beautiful. Thank you so much for linking this. I need to, That's really cool. Look at him go. That's really neat. Huh. Alright. Thanks for leaking that. So, that's crazy how planets go for. Nice to see it in motion. Yeah. We learned about that a little in philosophy. Super cool. Yeah. Okay. So, getting back to what I was saying, Ptolemy himself, wondered what was at the center right here. And there's, passages in Ptolemy. I used to read Ptolemy a lot when I was in college because I really found him fascinating. There's moments when you can tell that he actually understands that it's the sun. that's right here at the center of all these epicycles. And he just, I don't know, it didn't matter to him. If that makes any sense? It wasn't important to Ptolemy. Like, okay, what is the sun here? Is the rock there? That doesn't matter to him at all. All he cared about was just what he said was saving the appearances. I love Ptolemy. Saving the appearances. It's all he cared about, was making his system produce the results of what you see every day. That's all he cared about. He's just such a pure scientist. I love him. Long before Galileo, too. So, Copernicus. Other people thought that the sun was at the center. Other people came up with ideas. Copernicus is the person who I would say introduced it to the West. He spent time when he was younger traveling to the Middle East, where he studied, where he learned from Muslim mathematicians that, like, there was a way that you could describe the way the universe works, and it involves putting the sun at the center of the universe, right? You probably know Copernicus's theory. The idea was, okay, we're going to put the sun at the center, and then we're just going to have all of the planets moving in, quote, circles around the sun. So even the Earth now becomes just another planet, and it goes around the sun in a circle. That's basically his theory. The thing that gets left out of the details almost all the time is the fact that he stole the mathematics from basically non-Christians, and that's relevant because Copernicus was a Catholic, and it was extremely important to him to die a Catholic and not be excommunicated. And so he waited to release his theory until his death day. And I don't know, what I had heard before was that it was due to the fact that the theory that he was overturning was the idea that the Earth is at the center of the universe, and that had become kind of core to Catholic philosophy at that time. The Earth being at the center kind of reinforced the idea that this planet is special, that it's protected by God, and Jesus died for our sins, etc. Like, it all goes back to, like, Genesis, and, like, God created the heavens and the earth in 7 days and all that kind of stuff. But the point is, like, he shifted the Earth off-center, and that put the Earth not in the center anymore, and that went against, like, the Church's teachings about how the universe worked, right? Ptolemy's theory basically backs up the idea that the Earth is special. It's right there in the middle, right? Right at the center of attention. And Copernicus was overthrowing that. Now, I don't know if that's so much the thing, or if it's that the mathematics that he learned came from what people in his time would have considered heathens, right? I don't believe that Muslims are heathens. Would never say that. I don't really believe that. But in his time, the Catholic world believed that. There were crusades going on to literally, not at this time, but not much before it, to literally go slaughter people in the name of God, which is really messed up. What's the history of... So this was a big deal, and he didn't release it until he was dead, because he was afraid that it would get him excommunicated, basically, from the Catholic Church. So, science and religion constantly at war with each other in history. Okay, so, yeah, all of this with Copernicus was so engraved in my head from all those years in Catholic school. Yes, I also went to Catholic school, so my family's Catholic, so, like, yeah, not, like, practicing, but my grandfather took me to church all the time and stuff. So, anyway, that's his theory, right? But the thing about his theory that often gets left out is that he also used epicycles, okay? Like, he also used epicycles to make this work, because you can't... So for Copernicus, he said, basically, sun at the center... This is all you need to know about Copernicus. The sun's at the center, and the planets... Planets? Sorry about that. The planets travel in circles, we'll say, around the sun. Okay? They travel in circles around the sun. The thing is that his theory, this alone, isn't enough to describe how the universe works. It will not save the appearances like Ptolemy wanted to do. So, instead he had epicycles. So it's like, this is plus epicycles. And his epicycles were, like, even more confusing than Ptolemy's. Like, it was like not only was there an epicycle, but there was an epicycle on an epicycle on an epicycle. It was like 3 epicycles per planet just to make it work. This, like, kind of... Well, I mean, you can see it in that picture that Danielle shared. It's really... It's like a bunch of things traveling on gear wheels, right? So this part gets left out. I don't know why. I guess people don't want to make things complicated, and they want to. I think everybody wants to lie to you guys, honestly, every time I read a textbook. But yeah, stolen mathematics from a different world that he brought back to Europe, and he's lauded as a saint nowadays. I don't know. That's the truth of Copernicus. He's kind of a hack, you know. We live in Indo-European world, man. I don't know what else to say. What's a hack? Oh, a hack is like somebody that basically takes somebody else's work and pawns it off as their own. Eurocentric world, yeah. Eurocentrism is immoral. Yeah, it's the West, man. That's all I can say. It's like the propaganda of the West is why we say it's Copernicus who came up with this theory when it's actually a Muslim scientist that came up with it. You know what I mean? It's like, I have to tell you guys that because most of the things taught us are distorted or complete lies. Yeah, exactly. I mean, welcome to America in the 21st century, right? The Muslims of the Middle Ages were much... Yes, exactly, Kenny. Exactly. They were way more advanced. Ottomans hype. That's right. That is correct. Alright, so... It's all because the Ottomans didn't take Vienna, man. That's the reason. That's the reason why I'm talking about Copernicus right now. And the reason why Christianity didn't die in Europe. Because the Ottomans weren't able to break Austria. Anyway. Historical tidbits from things. Alright, so that's Copernicus, okay? He's not my favorite. I like Ptolemy a lot more. Copernicus is kind of... I don't know. He got the Catholics to wake up, I guess you might say, and say, you know what? The Earth's not actually at the center. Alright, so now let's move on to more modern times. Not much more after him, but we gotta talk about a guy named Tycho Brahe first. He's the kind of really important figure in this whole thing. So Tycho Brahe was an astronomer who kept extremely detailed data. We'll just say with just, like, tons of data. He was, like, the big data guy of his age. Long before it was, you know, more valuable than oil. So, he had tons of data, okay? And the other thing you need to understand is he was basically in love with Copernicus' theory. He's the metal nose guy. You know that physics name. That's right. He had a metal nose. I think he lost his nose in a duel or something like that. Like it was shot off, and he had a metal nose. Maybe I'm wrong about it. Is that it? Okay. Yeah. I don't know. I didn't... Most of the stuff I'm talking to you about today is kind of just from my head. It's not always... It's like, so I might be getting some of the details wrong. But Tycho Brahe was an astronomer with tons of data who loved Copernicus, and he basically wanted to prove Copernicus right. He wanted... I'm sure Julio told you all kinds of great stories about him. He had tons of data, and he wanted to prove Copernicus right. He partied like crazy and died because he couldn't pee. That's awesome. So, he has all this data, right? And he's got an assistant. It's not really his assistant, but there's a guy that works with him, let's say, and his name is Johannes Kepler. So Kepler was someone that he was very what's the word for it? He really wanted Brahe's data, basically. He knew he could do some work with it. Kepler was a mathematician, he studied astronomy, and he wanted Brahe's data, okay? And so he basically, like, at first he kind of, like, worked as an assistant for Brahe, but they had some conflicts, and eventually Kepler, you know, wasn't able to work with him anymore, went away, and then later in life managed to somehow get his hands on his data. I think some of it had to do with, like, fighting with his estate after he died or something like that, but Kepler eventually was able to get access to all this data that Brahe took. He was thirsty. I was thinking about Gollum in the Ring. Like, for Kepler, like, the data that Brahe had is, like, the ring to Gollum, basically, in Lord of the Rings. So Kepler finally gets access to this data, right? And so he gets the data, and he basically goes to work. He basically goes to trying to figure out if he can prove that he basically wants to... He basically takes this data and he tries to prove that Copernicus' theory is right. He was really, really trying as hard as he could to basically make Copernicus' theory work. Okay? He wanted the Earth at the center of the universe, or the Sun at the center of the universe. He wanted everything moving in circles, and he just wanted to prove that Copernicus was right. Now, he goes about doing that, right? He's got all this data. So what data does he have? The data he has is the location of where the planets are, basically. Just information about where the planets are on a given day, right? And what he starts to do is this. Then he says, okay, well, I know where the sun is. It's at the center, right? And everything that I'm going to look at is going to be measured relative to this. And he started looking at one planet in particular, okay? He started looking at Mercury. Good old Mercury. Mercury has taught us so much about the universe, it's unbelievable. So, Mercury is the closest planet to the sun. And it has some interesting features. But specifically what Kepler was doing was he said, I know where Mercury is one day, and I know where it is another day, and I know where it is a whole bunch of other days as well, right? He's got all this. I'm not really doing this justice. This one should be kind of more like here. Maybe he's got all this data about Mercury. And let's say that those points represent, they represent Mercury for him. Okay, those are where Mercury is at different points in time. And he said, let's try to make a circle, and let's have it go through all the points. It's like, well, I can make it go through those points, or I can make it maybe go through these points, but then it's like, if I do this, it's not really a circle anymore. If I do this, it's still not a circle. It's like, he kept basically saying, like, I want to have a circle, and I want it to cross through every single point. And he's like, well, does this work? Not really, I'm missing some of those points. So he, like, made it a little bit smaller, and he's like, okay, now I can get it to go through most of the points. It's like, that's kind of close, but what about this guy over here? And so he's like, well, I need to make it... You can kind of see the problem pretty quickly, right? And even to make it go through the points, actually, you'd want the sun to be right at the center, too, right? So if you force the sun to be at the center, you get even more of a problem, right? You guys get the idea? It's just like fitting a curve, right? And it just... He basically tried circles forever, but basically, like no circle could actually hit all the data points. Yeah, it's elliptical. Exactly. That's what he eventually figured out. So he basically set out, and this took him a really long time, apparently, like multiple years, of him trying to figure out, well, if it's not a circle, what is it going to be? And so he tried all these mathematical objects. And supposedly, one of his first thoughts was exactly what Ash said. Oh, well, let's just put an ellipse in here. What's an ellipse? Well, an ellipse is basically a circle, but it's kind of elongated, like this. And if you do that, all of a sudden you have a lot more freedom to hit all your data points here. And I don't know if I'll do a good job of this, but like maybe I can find a way to get ellipse to fit all these data points here. I don't know. Oh, see, it's going to have to be shorter on this side, isn't it? Like that. So you can start to see that, like, with the freedom of it not being a circle, all of a sudden, there we go. I basically hit all the data points, and maybe this is within the error bar, and so like maybe this one's a little bit off, but certainly looks a lot better than a circle was looking, right? And supposedly, this was one of the first things he thought to try, was an ellipse. But then he said, you know what, I'm not going to try an ellipse. That's way too common of a mathematical object. Like, certainly, this is really what supposedly he thought. He wrote this down. He's like, one of the first things I thought was an ellipse, but then I was like, certainly someone's already done this before. He's like, there's plenty of intelligent mathematicians that have come before him. Like, certainly, like, they've tried elliptical paths. And he gave up on it and tried some other curves, and eventually, later on, came back to ellipses. And so, this was, if you think about where we've come from here, Kepler basically was able to figure out that we were wrong all along. Aristotle once again led us down the wrong path. This word, the need for everything to move in circles, had basically held back all of astronomy for years in terms of understanding what was happening in the heavens. It was this problem, this first assumption, right? This is so important because in science, in mathematics, it's all about the assumptions that you make, right? It's all about, this is how you spell the word ellipse. It's all about the assumptions you make and understanding when you're making assumptions and being careful about testing those assumptions from time to time to make sure that you actually believe they're correct, right? And that first assumption was the thing that threw everybody off for so long. The need for things to move in perfect circles, the need for things in the heaven to be perfect, to fit one of Plato's forms. The perfect idea of what something could be for them was often seen in geometry for the ancients. And for them, one of the most perfect things in geometry is the circle, right? And while I can draw a perfect circle in a way by using a device like this, right? I can't do it by just drawing it freehand, right? I can say, that's a circle, and you can say, well, Is it though? Because a circle would have the radius the same everywhere, right? They really, really, really held on to that idea dogmatically for so long, and it just held back on astronomy. Just the fact that they weren't willing to try something else. Even Kepler wasn't willing to try this until the very end. But that's what we know now. That's the end of the story in a way. This leads to basically what Kepler's first law is. Kepler's first law is that all planets move in ellipses. And they travel on elliptical paths, and the sun is at what's called the focus of the ellipse, basically. That's Kepler's first law. We'll talk about Kepler's laws here in a second, but I'll stop right there. That's basically the beginning of the end of like kind of the history, and we'll now kind of open up the mathematics behind this next. Do you guys have any questions or comments? A few people typing. I'll look into this. Focus sounds like a conic section. It's about conic sections, yeah. Yeah, conic sections. So, yep. That is the history. Maybe we just take a break right here. So no circular motion, like no acceleration. Now here's the thing, Jesus. There is still acceleration for these objects. Absolutely, they are accelerating, and yeah, that acceleration is produced by a force, right? And that's where we're going with all this. Is like, what is now the force that actually allows Mercury to travel along this path? You know, what's the force? And you know, it's going to have to be a force, right? The only thing that makes things travel in a circle, like if you got a velocity this way, but your velocity's turning, then there must be a central force, right? And that force is the force of gravity. That's what we're going to learn about today, right? You have to have that force to allow things to go in a circle. So it's not circular motion, but you're still going to have centripetal or radial acceleration, right? Produced by this force here. No circle could pass through all the data points, so he used an ellipse. So I think this is probably just as good of a place as any to take a break, and we'll take a break until like 3:25 maybe, and then we'll come back and we'll talk about Kepler's laws, and we'll talk about Newton's theory of gravitation, and we'll do some problems if we have time.